Hello everyone. Here we are going to discuss how to use the Moody's chart or Moody's diagram to find out the head loss. Actually, this diagram is used for finding out the friction factor for different types of pipes. So this is what the diagram looks like. As you can see here, the x-axis has the Reynolds number and the y-axis has the friction factor. Now it will be different for different types of pipes, and the type of pipe is defined based on its roughness, and instead of direct roughness we are using a term called relative roughness. This relative roughness is defined as E by D or epsilon by D, where epsilon is the average roughness height inside the pipe. Now what does it mean is D is the inner diameter obviously, and this epsilon is, you can imagine, in a pipe where the inside will be having this kind of small roughness on both sides. So this roughness will have some kind of average height, although all the roughness elements will be slightly different from one another, but on average it will have some height, and that height is defined as this average roughness height epsilon. Now based on that, the relative roughness of the pipe is defined as epsilon by D. Now it's also a non-dimensional term, and the reason because we are turning it into a non-dimensional term is because we don't have to then worry about the units. If the roughness is given in millimeters or microns or inches, whatever unit is given, when we divide it by the diameter in the same unit, then we don't have to worry about what the unit was. And that's helpful because all the other axes are also unitless. Reynolds number is a unitless or dimensionless quantity, and similarly friction factor F is also dimensionless quantity. Now you can see several number of curves. These curves will be applicable for different values of relative roughness, like this, and based on the given pipe or the pipe material, we can find out what is the roughness or average roughness for that particular material. For example, for concrete, coarse concrete, it is 0.25 millimeter. For smooth concrete, it is 0.025 millimeter. Then for drawn tubing, which is the tubes that are made by stretching a bigger tube, then glass and plastic will have very small roughness, so you cannot even feel it. It's very slippery. In cast iron pipes or galvanized iron pipes also, it's approximately 0.15 millimeter, and so on. So for different types of materials, these different values are given like this. Now based on what our problem is, we'll have to first select what is the material, then select these values, one of these values, and then find out this. So let's do an example. So we'll start with this kind of a simple example where we have two tanks or drums, and they have water at different levels, and let's say the difference between this level and this level, so this difference is our head loss, and in this case let's say it is about 10 meters, and the length will take as 20 meter, and the diameter for this example, let's say it is 100 mm or 10 centimeters. So it's a about 4-inch diameter pipe, and in millimeters it is about 100 millimeter. Now in this pipe, if we want to find out what is the flow rate, then what we can do is, first we'll have to know what the pipe material is. For this example, let's say the material is cast iron, suppose, and for that the value of roughness is 0.15 millimeters and the diameter is 100 millimeter. Therefore, this value epsilon by d will be equal to 0.15 divided by 100, 0.15 by 100, that is 0.0015. So this is our epsilon by d. Now we'll have to choose the curve corresponding to epsilon by d equal to 0.0015. Now if you look here, this curve is for 0.002 and this curve is for 0.001. So therefore, in this available diagram we do not have a particular curve for 0.0015, so we can draw one, and this looks like a logarithmic table, logarithmic axis. That means difference between these are not very equal, so 0.0015 will be somewhere approximately here. So this is our curve. So you can, if you want, you can draw this kind of a curve using pencil and use that curve for carrying out the calculations. So this kind of a curve will be, we'll draw it by hand. So this curve will be used for our calculations. Now once we find this value, now the next stage is to find out velocity. We have to use the head loss formula, that is HF, head loss due to friction, is equal to FLV square by 2GD. Now HF we can find out, which is 10 meter. In this example, for simplicity, we are ignoring the loss at entry and the loss at exit. You can include them, but it will not make much change here. Now anyway, in this formula, now to find out the velocity, we'll have to take this to the other side, and V becomes square root of HF into twice GD divided by F into L. But the problem is we still don't know F, and if we try to find out F from our Moody's diagram, we'll have to choose this dotted curve, but the problem again becomes that we'll have to know Reynolds number, and to find Reynolds number we have to know the value of velocity. But velocity is the quantity that we are trying to find out, and how can we find velocity then? So now we are stuck in a loop actually. To know velocity we have to know Reynolds number, to know Reynolds number we have to know velocity. So what we can do is we can start with some trial value and then correct our results by trying different values. So what we can do in this case is, we have the curve, so we'll assume some random value, and to be on the best bet will be in this case to assume somewhere in this range. The advantage is that over this whole range of Reynolds number, the value of friction factor for this curve, because the curve is horizontal, so the friction factor value will be fairly uniform. That means if you find out the frictional factor value for, let's say your Reynolds number is 10 to the power 2 into 10 to the power 6, so that will be here, and corresponding to that Reynolds number will be the friction factor will be somewhere here, and that will be the friction factor even if the Reynolds number is 10 to the power 7 or 10 to the power 8. So for this wide range from this point onwards, the friction factor will be this same value of approximately 0.21 or 22, because this is again a logarithmic scale. So we'll start with that assumption that Reynolds number is somewhere in this range. It may not be the case, but we'll start with anyway. Now, so that means our Reynolds number is approximately 0.022. We'll see if that is correct or not. So RE equal to 0.022. So we'll use this value. Sorry, not RE, this is F. Now this corresponds to an RE value which is greater than approximately this much, which is, this is 10 to the power 5, this is 2 into 10 to the power 5, 3 into 10 to the power 5, then 4 into 10 to the power 5, 5 into 10 to the power 5, around 6 into 10 to the power 5. So if the Reynolds number is greater than 6 into 10 to the power 5, then this is the value of friction factor, and with that we'll start our calculations. So we'll use this formula to find out the friction velocity. Let's try it with Excel. This will also be an introduction to Excel for you. So in Excel, I have already typed in the values, that is E equal to 0.02, we have taken 0.15, right? 0.15, and diameter is 100, and these are in millimeters. Now E by D, that is relative roughness, will be given by this value divided by this value, and therefore in Excel what we can do is we can directly calculate using some kind of formulas. The formulas are very basic formula, very intuitive. So if we put equal sign before anything, then whatever we write after the equal sign in a cell will be counted as a formula. So in this case we want 0.15 divided by 100, so I'll type 0.15 and divided by this slash sign or oblique sign and 100. It will give us 0.0015. But in Excel you don't have to type in the values, because I've already filled the values in some other cells for my reference. Therefore I'll delete it now. Now I can, instead of writing the values themselves, I can simply put equal sign. After that I'll write the formula. In the formula I can simply put the cell address or the coordinate of the cell. In this case the cell that has the 0.15 value is in D column and in number 3 row. Therefore it will be called D3. So I'll write equal D3. So as soon as I write D3, it automatically highlights the cell D3 in blue, and the D3 has become, the text color has also become blue, and I want D3 divided by the cell that has this 100 value, which will be D4. D4. Now it has automatically highlighted it in red. If I type hit enter, it will automatically give us 0.0015. Now it is showing the value, numerical value. If I double click, it will show how I got that value, that is what kind of formula I have used. If I double click here, you can see the d3 by d4 formula is visible. Now the friction factor value, it's not 0.03. Now we have assumed some Reynolds number, that is RE. We don't know the value, but it is something which is greater than 6 into 10 to the power 6, 10 to the power 5 or 6, let's say again. Yes, 6 into 10 to the power 5. So 6 into this is only for our reference. Now, based on this Reynolds number, we'll find our value of friction factor as, what was the friction factor? It was 0.022, and from the graph it was 0.022 approximately. So we'll put 0.022 here. Now length of the pipe is 20 meter. I'll also put meter here, and head loss is 10 meter here. Now we want velocity, and for velocity we have rearranged that Darcy-Weisbach formula, and velocity will be given as square root of hf2gd divided by f into L. So we'll try to put this formula in Excel now. So V is equal to square root, and again I'll put some equal sign here. That means it will be a formula after equal sign. For square root, I cannot simply write SQARE root. It doesn't mean anything. Okay, so Excel has some commands, that is SQRT means square root. Now you can see below where I'm typing, it is already giving us some suggestions. So SQRT is actually a formula which is available with Excel. So I'll put bracket, and it suggests how to use this formula, SQRT, then within bracket put the number, and instead of number we are again going to put another formula. That means a formula inside a formula. So SQRT, the formula was square root of HF 2GD divided by FL. So I'll put HF. What is HF? HF is head loss. Here I have written it as capital H. So instead of writing 10, I'll simply click on this cell, or I can also put write the cell address, that is D10, but instead of typing in the cell address, I can simply click on this cell, and then the software automatically writes D10, that is the address of the cell. So that multiplied by, I still forgot the formula, HF2GD divided by FL. HF into 2 into G is 9.8 into D is diameter. Diameter is 100 mm, but we are writing everything in SI unit. Therefore, if I click here, it will take the values in millimeters, that is 100. So to convert it to meter, I have to divide it by 1000. So that is F into 2GD, HF into 2GD divided by F. F is in this case this value, divided by L is this cell. And typically we'll have to close this bracket, but we'll see what if we don't we forget to close this bracket and simply hit enter. You see, now it is still giving us the value V equal to 6.67, and we know it is in meter per second because we have entered all the things in SI unit. Now, since I forgot to give the bracket, if you look at the formula, now it has already filled in the bracket, because the developers from several years now have known, now they know that people often forgot this kind of brackets here. So the software has this feature that it will, in case of simple formulas, it will automatically fill in the last bracket. So that's how it works. Now we have found the velocity, but we found this velocity based on a friction factor which we assumed based on a trial Reynolds number which is about which is more than 6 into 10 to the power 5. Now we have to check whether that Reynolds number, this Reynolds number, is actually correct or not. For that, we can simply use this Reynolds number formula, which is rho v d by mu. So we can again use it, find it using a formula which is equal rho for water is 1000 multiplied by velocity is whatever we found out, v, multiplied by diameter is 100 divided by 1000 to convert it to meter, divided by dynamic viscosity, which is for water it is approximately 0.00089 Pascal seconds, which is the SI unit. And if I hit enter, it is giving us how much is it? 7 into 7 point, approximately 7.5 into 10 to the power 5. So how much did we assume Reynolds number to be? About 6 into 10 to the power 5 or more. Now we are getting it is 7.5 into 10 to the power 5. So that means, let's look at the graph again. Where is that value? 7. This is 10. This is 9, 8, 7. So 10, 9, 8, 7. If we go up, it's actually 7.5, so it will be somewhere around here. So if we go up here, then we'll hit the curve that we have drawn, that is this dotted line, somewhere around here, and corresponding to this, the friction factor is whatever we have assumed, because beyond this the friction factor doesn't vary much, it is almost constant at 0.022 here. Therefore our assumption was correct. This is, we can, for our reference, we can write down this is greater than 6 into 10 to the power 5. Therefore, okay, now this is the velocity of flow that we have found out. And based on this velocity, we can also find out the area. But this is a simple example, and I chose this simple example because that way we don't have to do more trials. But what if our assumption was wrong? That means we have assumed some Reynolds number, but after calculation that Reynolds number was not that much. So in that case, what will happen? Let's try, we'll use, instead of average roughness 0.15, we'll use 0.025 suppose, and diameter is now let's say 30 mm. Now instead of 30 mm, just to have a better value, 25 mm. Now this relative roughness is 0.001, and we don't know what the Reynolds number is, but we'll assume it based on the diagram. And friction factor, again, we don't know. Length is 10 meter, head loss is 10 meter. Now this is one thing to notice in Excel, is that here it is giving divided by zero error, also again here divided by zero error. That's because this formula is linked to this cell, this cell, and this cell is now having zero value, and in this formula that was in the denominator, and therefore it is giving that divided by zero error. Now we'll address this later. After we put in some value here, then this error will be fixed. Now let's look at what will happen here. The relative roughness in this case will be 0.001. So let's look at the curve again. For 0.001, we already have a curve, so we don't have to again draw this dotted line. So that's now not necessary. So we'll simply use this curve. For 0.001, now let's again say we have assumed that the Reynolds number, since we don't yet know it, Reynolds number is again greater than 10 to the power 6. That means from here onwards. So if it is greater than 10 to the power 6, then for this curve it will be again approximately constant at about 0.02 approximately. It can be 0.019, but let's assume it is 0.02. So using that value, now in Excel let's put friction factor value 0.02, and that's for a Reynolds number which we have assumed to be greater than, just like the previous assumption, 6 into 10 to the power 5. So this is our assumption that Reynolds number will be greater than 6 lakhs or 600,000. Now again, all these values, you see the values are already filled up automatically because we didn't remove the formula. The formulas were there. Now it is automatically filling up these things, which are so this velocity is 3.5 meter per second. Now the Reynolds number is how much? It is less than 100,000 or less than 10 to the power 5. It is 9.8 into 10 to the power 4, and therefore let's see here. Reynolds number will be somewhere around here. So for this value, the friction factor was actually, if we follow this curve, that is this curve, we'll get somewhere around here. And for this friction factor value, if we go to the axis values, it will be around this point, which is, say, again 0.022 instead of 022 instead of 0.02 that we have assumed. So now this is less than what we have assumed, therefore it is not okay. We don't have to write it. So what do we do then? Now we have found that the Reynolds number is different, and for that this value is now again different. So instead of 0.02, now we will put the next value that was suggested by the diagram, by the graph, that is 0.022 instead of 0.02. So let's put that value 0.022 and see what happens then. Now, is it giving us any other kind of change? For 0.022 friction factor, now the velocity is, instead of 3.5, now it has become 3.337, and Reynolds number is now about 9.4 into 10 to the power 4. So let's see where that lies in this graph. So this is 10 to the power 4, 2 into 10 to the power 4, 3 into 10 to the power 4, and this is 10 to the power 5. Somewhere around here it will be a 9 into 10 to the power 4. That means around this graph. Earlier it was suggested somewhere around here, and now it will be slightly towards the left, and we'll see that instead of going along this line, if we go along this slightly leftwards line, where it will get us is that it will get us somewhere around here. It's very close, and when it is very close, we'll see that the new friction factor value will be, instead of 0.022, it may be 0.0219 maybe. And if we put that, actually we can stop right here. That is, instead of 0.022, it is not giving us 0.023 or 0.021, because those values will be somewhere around here or here. But from the graph, we have seen that it is so close that it is not going to give us that kind of change, because one is here, another one is here. I think let's zoom in a little bit. If one was here, the other one was here. So therefore, they are not giving us a new, much improved value of friction factor. So whatever we found earlier, we'll just keep it, and we'll keep it at 0.022 and for that the Reynolds number is now 93 something, 93,739, and because of that, whatever we'll get, it is not going to be much different from this value, and therefore we'll be satisfied with this much. And now we have our answer, V equal to this much, 3.33 meter per second. You can find out the charge from this by, let's say, this charge Q equal to, see, this is only a text column for our understanding. If I put an equal sign at the end, it doesn't matter, it will just consider it as some kind of text. But if I put it before writing anything, that is at the beginning, if I put equal sign in a cell, then whatever I write after that will be considered as a formula. And here we want Q equal to velocity multiplied by area. So velocity is, instead of writing the value of velocity, I'll simply click on this cell, and the software will automatically fill up its cell address, that is D11, multiplied by area. Area is pi, that is 3.1416 approximately, into d square. D is 25 mm, but it has to be in meter, so divided by 1000, and this has to be squared, so I'll put a bracket, and square will be given as this power sign, pi d square divided by 4. So that is this much meter cube or cubic meter per second. So this is our answer. This is the discharge. So this is how we are going to use the Moody's diagram to find out this kind of, to solve this kind of pipe flow problems. So I hope you have understood a little bit about how to use this diagram, and also a little bit of Excel, how to use it. So we'll see you in the next class. Thank you.